Welcome, everyone. Welcome to the Fall 2024 industry curriculum of the USACM TTA on the large-scale structural system and optimal design. So today, with the great pleasure, we have introduced two experts from the industry to give us this first presentation, first curriculum in this series. So let me introduce them in a second. So before that, I just want to advertise for our large-scale TTA. So here we have the 4 members in the TTA management team. And starting this fall, we'll start this industry curriculum. We'll have several seminars coming in place to talk about the different advancement problems and challenges coming from the industry perspective. So stay tuned for that. And if you would like to start sharing the slides from your side, I will start the introduction.
Yes, of course.
Yes, thank you. So today we have great honor to have 2 experts from Ansys. We have Michailidis, Georgios. He's the lead R&D engineer from Ansys. He studied the civil engineering at the Aristotle University of Thessaloniki, and he did postgraduate study in the applied mathematics at the National Technological University of Athens, and obtained his doctoral degree from the École Polytechnique of Paris. So he studied at the Renault Technocentric and Center and 2 French universities. So since 2017, he has worked as an R&D engineer at the structural optimization team for Ansys. We also have another speaker. He's a Sebastian Stahn, and he's the product manager for structural optimization from Ansys. So Sebastian studied the mechanical engineering at the University of Kansas and University Politecnica de Madrid. And since 2008, he has worked in different roles and is currently the lead application engineer and product manager for structural optimization for Ansys. So with great honor, let's welcome them to give us this curriculum. You have the floor.
Thank you very much. So good afternoon, everybody, and thank you for attending our presentation. First of all, we would like to thank the organizers for inviting Ansys to present in this colloquium of the US Association for Computational Mechanics. My name is Michailidis Georgios, and I work as a lead R&D engineer for Ansys, together with my colleagues, Oliver Exler and Alexi Fork, who is currently the team leader.
And I'm Sebastian Stahn, and also glad to be here and to present you about what we think about industrial applications using this technology. And as I'm acting as a product manager and see how we can move the things forward from all sides. Yep. And today we're speaking about it. Yep. So first of all, there's a lot of challenges for the industry nowadays. We have all the sustainability, and we need to look for weight, for mass, and for fuel consumptions, energy. So we need tools, and one tool is not enough. So we offer a range of it under the structure optimization roof. We have the topology optimization, lattice and free morphing. For the topology optimization, we have the well-known density method. So this is a quite old one. And we have the newer level set method, which acts a little bit differently. And we have also put it into the GPU-powered framework of discovery. So we can run it in a really fast time, as we will see later. The lattice optimization is known from additive manufacturing, I think, normally where we're just substituting the mass by some voids. And the free morphing is especially interesting because we're looking for strengthening shell designs. And as things get more and more less noisy, some parts like compressors are getting more attention, and we can use the topography optimization for that with regards to the equivalent radiated power, what we can minimize to make it low noise. And of course, to bring it also to the solid bodies where we can then have, through moving nodes on a surface, less stress and a higher lifetime. That's important. And at the end, we can combine everything what you can see on the screen for the best possible assembly design. Here we can see this kind of free shape or morphing and topology optimization. We need several workflows for that. So the one is the design validation. Then we have the chain of optimizations where we're just using different kind of methods to get the best results. The most important and biggest pain point, STL, to cut to solid parts. And we need to check if we can really manufacture it. 3D printing is quite expensive, and we have a simulation suite for that, where we can check the positioning and as well as the support structures to have the right printing time. Also, this kind of compensation of distorted geometries if needed. Yeah, let's have a look at the first one. So this is how we are presenting our workflows. We have the structural analysis at the one part. Then this is feeding our topology, or let's name it structural optimization. You have the free choice, of course, what you want to use. So here we have topology optimization. And finally, we have design validation, where we check if all requirements are met.
Now, one may ask, why should I validate a design, since topology optimization performs an analysis at each iteration? So first, let's mention that using density methods, it is inevitable that your design will contain some intermediate densities, since implementing projection methods based on some continuation approach that is frequently presented in literature is prohibitive in terms of time for industrials. Exporting a shape based on a density threshold is expected to have some impact on the values of the criteria serving either as objectives or as constraints. This effect is significantly reduced, of course, using the level set method. However, even in this case, since a fixed mesh is used and combined with some sort of ersatz material approach for the exterior part of the shape, some criteria, such as the stress, for example, may be computed with reduced precision. As you can imagine, a key ingredient for the success of this step is the smoothness of the optimized shape. The smoother the shape, the easier it is to reconstruct the mesh. However, smoothness introduces new challenges related, for example, to the rate of convergence, to the geometric details that finally appear in the optimized structure. For example, it's possible that the customer expects to see some thin ribs. And finally, there is a compromise to reach based mainly on the customer's experience.
Yes, and if we look at another workflow, what you could use, and we see here a workflow about as input, we're running in rigid body dynamics to get really dynamic loadings onto those 4 points for the static structural optimization. And then from this shape, we're using a topology optimization to reduce the weight and also, of course, keeping all kind of constraints, what we're giving this kind of shape. And here the big question is it really working in a way it should? And so in the next step, we're looking then at high loaded parts with a fatigue analysis, for instance, is then morphed with the free morphing technology to get a higher lifetime at the end. And so we can improve or reduce the stress by 43%.
Now, beyond the aforementioned challenges concerning the mesh reconstruction, we need to highlight an additional difficulty for this step. And this is that with the exception of the level set method, which is of geometric nature, shape optimization uses different variational methods than density-based optimization. And in order to make this workflow work, you need to cover a comparable range of criteria for both methods, which is quite challenging.
Now comes the biggest pain point, I would say, for the industry. Imagine to get such a part back to CAD. This is really taking hours, sometimes in the past at least. So we have another concept. So we have a tool which can create with one click this kind of part back into a NURB surfaces as a solid part. And as we know that sometimes we need to change it a bit, we introduced the so-called subdivision modeling, where we are creating patches also with an automatic routine. And those patches we can then manipulate afterwards. We can add things. The boundaries are coming clear across. We can move on all kinds of surfaces to improve or to change something. Or even, if you can see it here, if there's some kind of a bridge needed for the post-processing, we can just add it. And that's it. So that's the magic. And then finally, we can convert it back to a CAD.
Now, achieving robustness and precision in this process is also a difficult task that requires collaboration between optimization and CAD experts. In vague terms, we could say that the bad geometry would require to deviate significantly from the optimized boundary in order to create a proper CAD design, which can lead possibly to significant deviations in terms of performance.
Yeah, so let's have a look at the additive manufacturing workflow. As mentioned, it's important to have a simulation up front of the printing because it's expensive. And we need to look for orientations, strategies, scan strategies, support strategies, you name it. So we have everything connected and internally here for us, for the customers. And to give you an idea what was the challenge here, we faced that this kind of part, what we can see here, it's a really finally optimized part with milling. And the requirements were that this part weighs around 200 grams, should be even optimized even more. And then we get it down to 127 grams in titanium with our technology. And we have also sponsors for that, which helps those students to print those parts as a kind of a sponsoring package so that they can really take it and use it in their competition. And here you see it in action. They put it on the top left part, installed it, tested it, and it was also run in their racing series. And another part, what you can see, their electric motor is held by the part and the tire and the brakes. And we did it also with the same approach of discovery at the end and get it back to CAD. And the requirements were to have a car which is really lightweight, so 204 kilogram. I think they ended up at 180 if I got it right. I talked to them. The performance is always the same, and yeah, the speed is 2.5 seconds from 0 to 100 kmh. It's 0 to 60 mph in America.
So this completes a general overview of how structural optimization is implemented in Ansys and which are some general challenges related to the need of complete and efficient workflows. Now let's focus on some functionalities that prove to be important for industrials through our experience. And let's start from manufacturing constraints, which, as you can imagine, is a crucial component for real-life applications of structural optimization. Now, beyond standard constraints that are frequently met in literature, such as casting duration constraints, overhang elimination, feature size constraints that we dispose and provide to the user, there are also some manufacturing constraints that derive from the functionality of the part. Consider, for example, this clutch design here, fixed at some regions in blue, and where a force is exercised in the inner surface here in red. And suppose that one wants to minimize the compliance subject to a volume constraint. Now, if you perform topology optimization on this example, you will probably get some perforated design like the one shown here in this figure. But what if, for example, the region that is shown here in green encloses some liquid? And for this reason, we need to take a watertight design at the end that envelopes these surfaces. This is the role of the so-called housing constraint. Adding a housing constraint to the optimization problem guarantees that the selected surfaces will be enclosed in the optimized design. It doesn't mean that these surfaces are excluded from the optimization. They are still optimizable. However, the optimized design must enclose them, as you can see here in the new optimized shape that we get adding the housing constraint. So this is the evolution of the shape. You see that there is no perforation. The initial surfaces here in green, they are enclosed into the design. So this is different from the so-called no-hole constraint that exists in literature and is frequently combined with some casting direction and handled with additional controls. We have an in-house derivable formulation that is integrated in our optimization algorithms without any problem. So now it's true that topology optimization allows for great design changes and significant gains, but it's still true that a lot of work on structural optimization in industry still concerns the so-called shape optimization, where the connectivity of the shape remains unchanged. This is either due to the fact that industrials may not want to add some geometric complexity in some parts, usually coupled with some increased cost, or just, as we mentioned before, because they want to optimize just some slight details. We have invested great effort to construct our own machinery for mesh morphing, which can achieve significant mesh modifications while keeping a proper mesh quality, as we can see in this example here. Now, consider this part, which is fixed at some regions in blue, distributed cyclically, and where there is a remote rotation, imposed rotation at the top surface here in yellow. And one searches to maximize the reaction force at the fixations. It's a sort of stiffness criterion, subject to some mass constraint. There are some regions here in red that are non-optimizable, and only the part in blue is allowed to move and be optimized. And as you can see here from the animation, you can verify that our morpher can achieve significant shape changes while keeping a proper mesh. Now, the robustness of the morpher, even if it is exaggerated in this example on purpose, of course, the robustness of the morpher is a key issue for industrials, since, as you can imagine, they are not happy at all with preparing a model and a setup and then seeing the optimizer crashing prematurely after some iterations. Now, this becomes even more challenging when adding some design restrictions, which is a common need for industrial applications. One example of this kind is the so-called in-plane morphing restriction, which imposes an in-plane deformation for the selected surfaces. So consider again the same example as before, and we will add the so-called in-plane restriction for the surface that appears here in red. That means that this surface is allowed to move only in plane and not perpendicularly. So you can see here in the optimized result that this surface has remained planar, and you see that this is achieved throughout all the optimization process. So you see that this surface here just moves in the plane and not vertically, and still the morpher can achieve very significant shape modifications. Parallelly, another example of industrial manufacturing constraints is the so-called extrusion restriction, which aims to impose an in-plane, we would say, reshaping of the body, somehow mimicking a 2D-like deformation. Consider, for example, this shape here, which is clamped at two regions in blue, and the force is applied on the right part in red. And let's say that one wants to minimize the compliance subject to a volume constraint so that the volume is at most equal to the initial volume. You can verify in the initial design that the optimizable domain here in blue, it has almost a constant cross-section in the y direction. And if you run the optimization without adding any constraint, you would see that, of course, there is no reason that these cross sections will remain uniform. Okay, they will change according to, in order to optimize the criterion. So at the end, you will not get, in general, uniform cross sections. But if you add an extrusion constraint in the y direction, you will see that the cross sections remain uniform throughout the optimization. Now, the important part is that for this, we don't need the mesh to be uniform in the extrusion direction. We have our way to apply this constraint for general unstructured meshes. Okay, Sebastian?
Yeah. What is the next challenge here? So everyone is looking for ribs because ribs have the best stiffening effect by having a really lightweight. So the thing with the ribs is we need really small meshes because we need at least 4 elements through a rib, right? So that's the need for it. And doing it with other methods can lead up to calculation time for this part around 30 hours on a cluster. So this is not unusual. And you can also see on the right-hand side this kind of small element size with 1.15 millimeter to realize this kind of rib structures on the left side. With the power of the GPU, we can then use it with a method called automatic mesh refinement.
Yeah, so many customers want to use this GPU solver for such examples in order to profit from the accelerated finite element problem resolution. But however, an optimizer contains more than a solver. And for some of these parts, an analogous acceleration is very difficult to accomplish. In order to achieve better time rates, as Sebastian mentioned, we have explored and implement by default an automatic mesh refinement technique that allows to refine the mesh during the optimization until reaching the user-defined mesh fineness.
And here we can then see some application of this feature. So the scene bell crank is run in our tool with the GPU driven, and it's then doing as needed this mesh refinement to really get down to this really fine truss-like structure. And this is doing it in 5 minutes on a graphic card. And even it is also fast at the end for this part. You can convert it to the SDL. It's one click, and then you click on the faceted data, and you just convert it to the sub-D. And then the script is running in the background, which gives us, with one click, this result. And as seen at the beginning, we can also change, modify any kind of locations if needed. The part itself is transferring the power from the tires horizontally to the damping system, what we can see in the middle of the picture.
Okay, so now beyond the mesh discretization, it can be that the mechanical analysis is inherently also time demanding. Consider, for example, the harmonic analysis, which is frequently encountered when treating noise, vibration, or harshness problems. In this case, there is some part like an engine that vibrates, and we search to optimize the performance determined by the solution of the vibration equation that we see here. M is the mass matrix, the damping matrix is the C, K is the stiffness matrix, and you have a loading, a harmonic loading here, and U is the displacement field. Now, for harmonic excitations, like here, we are interested for the steady state part of the displacement, and instead we need to solve for every excitation frequency omega, this discretized system that you see here in the bottom. Now, for typical industrial applications, they involve very large frequency intervals of the order of 200-300 Hertz, as well as fine discretizations in order to achieve the required precision. It is typical to have 100 or even more excitation frequencies to examine. Solving for each frequency and compute this discretized equation and computing an adjoint state is prohibitively time-consuming. For such cases, it is common practice to work using the modal superposition method. In short, what is done in the modal superposition method is that we compute a reduced set of eigenvalues and eigenvectors here, and then try to decompose the displacement on this reduced basis. Now, if the damping matrix is diagonalizable, it is trivial then to compute the coordinates in the new reduced modal basis. Now, if you use this approach, instead of treating directly the displacement field, you must compute derivatives for the eigenvalues and eigenvectors of the reduced basis. Beyond the difficulty that deriving eigenvectors can bring, which I will not detail in this presentation, it is common to find more than 10 modes inside the specified frequency interval, which means that you must compute a derivative for each of them at every iteration of the optimization process. This is not necessarily prohibitive as before, but for sure it is still very time demanding. And for this reason, we have developed efficient ways of approximating the adjoint states that lead to a significant reduce in terms of computational time, keeping a sufficient precision. These techniques are implemented for all the criteria related to harmonic analysis. For example, for 3D solid parts, we dispose 4 criteria related to a notion of dynamic compliance, that is the input power, the input work, the average strain and kinetic energy. And we also provide the possibility to the user to build a composite criterion that depends on the displacement amplitude using what we call a user-defined criterion. Now, let's explain this in short. This is a very practical way to build a formulation for some criterion following a sequence of choices and reductions. For example, the user can go to a harmonic response analysis, add a user-defined criterion, name it, for example, displacement, and then follow a sequence of choices. Define the scoping, that is the region where the criterion is applied, a node, an edge, a surface, a body. He can choose a base result between a displacement, velocity, and acceleration for harmonic analysis, and then follow 3 successive reductions. First, a component reduction that transforms the base result into a real scalar field that depends on the location and the frequency, for example, the X component of the displacement. Then a spatial reduction that transforms the previous field into a field depending solely on the frequency. And finally, a frequency reduction that returns a scalar value for our criterion. So starting from a complex 3D vector field, which is the base result, we get a component reduction and we get a real scalar field that depends on the location and the frequency. For example, the amplitude of the displacement in the X direction. Then we get a spatial reduction, which reduces the scalar field that transforms the field to a scalar field that depends only on the frequency. And finally, a frequency reduction that provides a scalar value. That's the logic of our user-defined criteria. Let's see an example here. Consider the bracket shown here, which is composed of about 500,000 linear tetrahedral elements. It is fixed at some regions here in blue, and there are 3 forces applied at the regions here in red. There is a frequency, a large frequency interval from 4 to 9,000 Hertz, discretized in 200 intervals. And so by default, mechanical will consider all the modes up to 2 times the maximum excitation frequency. That means up to 18,000 Hertz. For the initial design, this corresponds here to 15 modes. And we have checked that during the optimization, this number for this example fluctuates between 15 and 20 modes. And so what we do here is that we have some exclusion region here in red. We have a pull-out direction. We have a housing constraint for this region here in red. And we search to minimize some average displacement criterion for the regions where the forces are applied, subject to a mass constraint. So it's a heavy problem. And here is the optimized shape that we get after 57 iterations. You can see here from the evolution that no perforation appears thanks to the housing constraint that protects the lower surface. And the algorithm converges after approximately 5 hours using 6 cores, which is quite satisfying for the specific problem setting. For topography optimization, we also provide the possibility to optimize the so-called equivalent radiated power that you see, the formulation you see it here, which depends on the normal component of the velocity. This dependence adds an extra difficulty when deriving the criterion, since ERP may be defined as well over an optimizable surface, as you see here, the region in blue. And then this exterior normal vector becomes also shape dependent. So if you consider the optimization of this cap, which is clamped at some points in blue, and there is a force harmonic excitation on the regions in red, and you want to minimize the equivalent radiated power subject to some volume constraint, and you are only allowed to move this surface here in blue. You see here the optimized shape that we get, and you see how the equivalent radiated power reduces significantly. So the blue curve corresponds to the initial design, and the yellow curve corresponds to the optimized design. You see how this has been reduced significantly over the excitation frequency interval.
And this brings us to why not mixing it up? So here's a special case. The steel hug has a really small displacement allowed only. So just running a topology optimizing on the aluminum block would fail because the requirements from the steel are too high. So by using an optimization, we allow that the shape optimizer also at the same time can modify the steel hug, and so that then it's possible to optimize this complete problem, which is before that not realizable based on the constraints.
So you see here the evolution of the optimization. The lower part is optimized with topology optimization. The upper part is optimized with shape optimization. They are optimized simultaneously. And the difficulty here is principally technical and concerns the necessary adjustments for the efficiency of the optimizer. So this example converges just after 30 iterations, which is it's just a few iterations, let's say, for such a problem. And here you can see another example. The upper part is the same clutch that we have seen before, and now it's mounted on a cell structure that is optimizable using topography optimization. We minimize the compliance subject to a volume constraint, and we keep the housing constraint for the clutch on top. And here you see the evolution of the two structures, the simultaneous evolution of them, and we achieve a convergence after about 80 iterations. 80 iterations is very normal for let's say for papers in literature, But for industrials, believe me, it's almost limited.
And then let's revisit it and let's name it generative design. So as we stated, we need this kind of ribs for really having a lightweight design and to fulfill displacement constraints on the bottom of this kind of device, this cap. And as it takes a long time normally, so we have a tool in place with the GPU power as we have shown, and we can use it now to bring it to the cloud and run all those 12 of them in the cloud in an hour, and we get back it, and we can also track it for kind of monitoring for this displacement constraints. And this is really a game changer then for the industry because they can explore a lot of things with a lot of power from the graphic card. And finally, speaking about machine learning, AI, whatever is the new name for that, you can run, as we have seen before, a lot of designs. Here is a bracket. It's well known, I think. And we run, I think, 50 or 100 designs with different kind of positioning of the fixtures, some safety factor which should be addressed, and different materials. So we can think about what if studies. And what you can see here is real time. So we're feeding a reduced order model at the end. And this reduced order model gives us all kind of possibilities based on a few calculation. And this is our generative design by intention. We can tune in what we need and we get a response immediately.
So this concludes our presentation. Thank you very much for your attention, and we will be happy to reply to any questions.
Thank you so much, Georgios and Sebastian, for the very informative and interesting talk. So now we have some time for questions and answers. First, do we have any questions from the audience? If you have any questions or curiosities, feel free to jump in or type it in the chat. So one thing I was curious is it's great to see that in the beginning you mentioned that some comparisons between these different types of optimization, for example, the density-based optimization, the level set, and later you also brought up the shape optimization. Do you have any suggestions or any comments on in which scenarios that one would be preferred than the other one, and which one would be preferred from the industry perspective or from the user's perspective?
Yeah. So I can try, and then Sebastian can complete if he wants. So first, topology optimization is mostly used to get a fast design concept, okay? And as we said, then it may be changed with other optimization types like shape optimization for a more finalized, let's say, result. Now, if we stay in topology optimization, as we said, we use different methods because we have the density and the level set method, because we really believe they can be complementary. Some people see it as antagonist. We see it as complementary methods. The density method has its own benefits, like it can perform very fast modifications, and it has its own drawbacks. For example, it has intermediate densities that can lead to a different result after the post-processing step. Level set is the inverse. It requires a more heavy machinery. It has less freedom to perform changes, but it can it's more, let's say, it's closer to the final result that the user will get. And then shape and topography optimization, in any case, it refers to cell structure, so it's something different. But shape optimization is mostly a type of optimization for finalized design. So it's something at the end, let's say, of the optimization.
That's great to know. That's very insightful to hear from your perspective. And so we have some questions. Let's get into them first. So the first question is, feel free if you want to turn on the mic and directly ask. So.
Oh, sure. Yeah, I really enjoyed the presentation. Thanks for giving the summary. I was thinking about other types of optimization problems, inverse problems, optimal experimental design, etc. Does Ansys have any tools for those kind of things?
It's OptiSlack, like the Sebastian. So the
I
tool
try
do
to
that.
understand the question. The inverse problems. Can you? I'm just not. You don't mean a parametric optimization. Is this inverse? Or is it?
Yeah.
Is it this? Yeah, we have for parametric design. We have something, and the last model what we have seen, we used our parametric optimizer for changing values, materials, densities, for instance, safety factors, and we run and we get a meta model of prognosis. It's the name for us, a response surface for that. And this response surface can then predict any kind of values and parameters on it and possible shapes. And we can call it machine learning. This is machine learning at the end. And some could also call it artificial intelligence. So that's what if this is what you mean with parametric design, we can mix it up and we do it also.
Oh yeah, that's really interesting. It's kind of like a surrogate model in terms of geometric / material parameters.
Yeah.
So exactly.
It's called
Gotcha.
OptiSlack in Ansys. So it's not done by the same team that does the structural optimization, but it can be coupled also.
That makes sense. Yeah.
So just as information on my LinkedIn profile, you can find something where I presented the cap with topography, what Georgios has shown. And in this video, I show how it is done, how it is built up as this kind of combined model. So you can find it on my LinkedIn page if you want. Otherwise, give me a ping and I can point you to that.
Okay.
Along in the same direction, just want to follow up on the inverse design. For example, will there be some capabilities of let's say we have some right now we have the minimization of the weight or maximization of the stiffness. Is there any capability to say we prescribe a certain type of properties to achieve, and then we solve that inverse problem to get a design to achieve that precise property?
Yeah, you can have, let's say, some you can build your own criterion in order to have you mean to have some target, let's say, displacement or something. Okay, so you need to create an objective function which is a target displacement to achieve. Okay, this is, I suppose, what you mean. This is something that we plan to do soon, so to give the possibility to provide your own objective function or to construct in an easy way your own objective function and use it. So in this case, it would act like that.
Sounds great.
And maybe just to add, because I see fracture as the point, we support, of course, the stress minimization or stress limitation for that as well. And with the maximum principal stress, we're addressing directly the fracture. So this is what our industry is telling us. The maximum principal stress is what is the cause for fracture, and we can take it into account.
But yeah, concerning the question is that our criteria for the time being, we mostly tackle linear criteria, as Sebastian said, stress, dynamic problems, etc. But linear, from the non-linear part, we handle with some of the methods, not with all of them, contact and some and the accumulated plastic strain. where we use some heuristic way to do that. We don't compute right gradients. And so non-linearities, we are planning to attack some non-linearities in the future releases, but for the time being, not fracture or fracture propagation.
Okay, I see. Sounds great, though. It's great to see the future planning. Yes, I think the next, go ahead.
Yeah, the question of breadth. So which capabilities take advantage of the GPU? So as Sebastian mentioned, our GPU solver addresses topology optimization with the level set method. So it does not address the other types of optimization. It's topology optimization with level set method. So again, there are several static criteria, linear criteria that are addressed, some modal criteria, and in every release, we try to expand these capabilities.
Thank you. Thanks for responding to that. I had another question, since I don't see any more in the chat yet. Can you talk any more about your conversion from STL to CAD? I know this is like you said, it's a huge bottleneck for a lot of people, and you know, it looks like you have a one button press solution for this. Is it how robust is it? How you know, can you just talk a little bit more about it? Because that's a huge capability.
I mean, it's not working 100% of all times, but we are good in the 80-90% of it. So it's depending, the level set in itself creates a really smooth surface, and we're handling on a graphic card, just to give you a number, it's a meshless approach, and we juggling around 10 to 20 million elements on it. This is, I think, quite okay. And based on this kind of refined meshless mesh or elements, it's quite smooth, the surface. And if we do it in discovery, our rate is quite high. If you bring it, for instance, with your own approach, which is not so smooth, the surface, into our program, then I can't guarantee that it's working always. But let's say with this kind of sub-D modeling, it is a kind of creating a cage around your problem, your STL, and it's patching it from the outside. It can go over some kind of small problematic areas. It can patch over it. And so this is our way to go if it's getting really complex and complicated. So, and it is ongoing improving. So we are quite happy, and we're never at the end. It's a mountain without a top, I would say. Yes.
Yeah, no, that's a hard problem. It's pretty exciting that you got as good a capability as you have there. Will your meshless approach, will it allow you to also identify analytic surfaces that may exist, or does it just always force NURB surfaces on everything?
All right. So I would say that the back to CAD process is not performed is performed in collaboration with a team that works in discovery. So we are not experts in CAD. Okay. So we collaborate with them, but it's not our team that does the back to CAD process. And so I'm not sure that I can reply right to exactly to your question, but I would like to add something that when you do the back to CAD process, I mean, I'm sure that in next year, the rate that Sebastian mentioned will even increase, and because we work on that. And just to mention that you may see, I mean, the rate of success is not, let's say, the only criterion, because you may use some criteria for the back to CAD, some tolerance for the back to CAD process that may allow you to increase the success rate. The question is, are you really close to the optimized geometry, or do you take a big tolerance in order to be able to perform the back to CAD process? Because if you take a big tolerance, you may deviate significantly from the criteria that you have computed during your optimization, and you don't want that. So the success is to achieve both a high rate of success and stay as close as possible to the optimized design. And this is what we strive for, and this is what I think makes it a big success for our structural optimization workflow in general.
Yeah,
But I'm sorry that I
makes
cannot
sense.
reply to the question of the analytic surface because I'm not a CAD expert, okay?
No, that's fine. And what you said there makes sense. It's good stuff. Looks really good.
Thank you, Brad, for the questions. We have one more question. I think it's related to something that Georgios mentioned earlier about fracture. George, would you like to directly ask? Or otherwise, I can ask on your behalf as well.
No, I think the question was answered. You're
Yeah.
planning on implementing something in the future. I don't know, was XFEM or cohesive zone methods, or what in particular are you planning on implementing in terms of modeling the fracture itself, or are you not going to be modeling fracture at all?
Yeah, I mean, as Sebastian said, okay, we don't, I mean, we do not handle fracture as an analysis, okay, as a direct analysis, so a non-linear analysis, including fracture. So for the time being, it's not, let's say, it's not in our immediate plan to include such analysis. So we started tackling non-linearities in general. We plan to include all the more in the near future, but I think fracture and fracture propagation, to be honest, I think it's very difficult for topology optimization. I mean, it's very difficult to achieve, in my opinion, a very high rate of convergence for such non-linear criteria.
Yeah, there's been some work. It's basically I think
Yeah.
cutting edge. Like you've used Phoenix Top Opt which include like an phase field model fracture. So it's coming around. I just was wondering if industry is going to be going in that direction.
We have not really received demands on that.
Okay. All right. Okay. Thank you.
Yeah.
But, and maybe just as an addition, we have, of course, smart fracture in our portfolio for another simulation. We have fatigue tools for it, and we could use this kind of sub-D modeling. If we see a spot with a validation which is prone to fracture at that point, we can just go back into the sub-D and we can morph it, or we can use this kind of accumulated plastic strains when it's coming up for the spots, and we can mitigate this accumulated plastic strain with shape optimization, also with nonlinear material. So let's say it's not perfect, but let's say our workflow is more about investigating, validating, spotting, and then let's remove the accumulated plastic strain out of the model, and we did it with this kind of knuckle example what we have seen. There is a story around it, which we also can share. So just doesn't fit into the frame of the time. Thank you.
So I have a related question in general. So for example, if there are some new algorithms or capabilities that came up from the, let's say, academia, what would be usually the collaborative mode or collaboration mode with Ansys, with the academia? Would there be some suggestions of if say someone develop a new computational algorithms that could be potentially of interest of Ansys?
So I would say that first of all, we follow very closely the literature, okay? So be sure that we follow very closely literature, and we know very well the work from some professors that are even attending the presentation now. And so I think that the interest, let's say, I would say from academia in today, I would say that is mostly on problems that are difficult to treat, like I would say non-linearities, for example. Okay, I would say nonlinearity. So finding efficient and robust ways to treat nonlinear problems is something that is quite interesting for us. This is to extend, so because the real problematic, I think, today is to extend the range of application of topology optimization beyond, let's say, linear problems. There is a limited application for nonlinear problems, or for other disciplines, let's say, like the coupling, structural acoustic coupling, all the stuff. So I think this is where the interest from academia focuses for us.
I see. That's great to know. So in general, the more efficient ways of handling different types of nonlinear problems would be something in general topics of interest.
I think so.
That's great to know. Do we have any other questions from the audience? So I think we have pretty good discussions, and it's great that you have some time left for us to ask those questions and discussions. Okay, so if there's no other questions, then let's thank our speakers one more time. Thank you for your wonderful talk and giving us a lot of insights and comments from the industry. I think we all learned a lot of things today. And I think just want to take a few seconds to advertise our next seminar for this series. Our next seminar is actually going to be in 1 week. We have it on November 13th, exactly at the same time. And we will have Dr. Simon Xu from General Motor Corporation to give us a seminar. Okay, so with that, let's conclude the first industry curriculum. Thanks so much again, Georgios and Sebastian.